Okay. Okay. Well, still missing 5 people. It's not so bad. Okay. One thing I've noticed in just about any class as the semester wears on, that so I like to make sure as much as possible that everybody's here, especially when it's not quite as large a class, and that might lead me to start a minute or two late. But then, I don't know, subconsciously you guys pick up on that and then go ahead and show up a couple minutes late. And there's a certain creeping going on where people just start showing up a little bit later, and then by the end of the semester, a significant amount of a percentage of class time is lost. And I noticed that happening in 285 last semester. I'd prefer to not have a repeat of that here. So we're still missing, well, okay, only 2 people in Hattiesburg and 2 people in Gulf Park. So please try a little harder to get here by 3:50. I know for some of you that is a tall order, so I understand that, but especially those of you who do not have a class during the period before. Okay. Next, let's see. My plan for this week is to finish covering Chapter 6 on Polynomial Interpolation. And then, after that is when you guys really should get started on the homework for that chapter. And that is one thing that motivated the, okay, I admit, semi-bitchy email that I sent last Friday. What? Yes. Thank you for confirming that. So, yeah. I'm sure you have. I'm sure you all have. But I just started thinking, oh my God, at this rate, we're going to be on homework 2 forever, and you guys won't care if I even cover anything else. And maybe you don't, but I have to. And sure enough, since then, a few people have submitted. But that still means that the majority of you not. But that's okay. You have the whole week, and then you really should segue as much as possible directly into the next homework on Chapter 6. Now, one thing to keep in mind is in the first 2 homeworks, I assigned every single exploration there was in those chapters. I have not this time, so check the list closely. I tried to show a little bit of mercy, just a little. For instance, and the thing is, I already got a question on one that I had not assigned. I admire your spirit, but don't torture yourselves. And what I said about the homework 2 still applies for all other assignments. If you send me good questions, then and I have a pretty low threshold for that. I'm looking to show that you did the reading, then you can get exempt from the concept checks. And I put in some recommended deadlines to wrap up the whole thing by the Tuesday after fall break. That's the 24th. So after I finish Chapter 6 this week, next week I will start Chapter 8. That will not be on the midterm. But I'm still going to be talking about polynomial interpolation, so I think you might find it useful. That's a long chapter that I'll have to finish up after fall break. So the schedule, has been adjusted. So, the dates are out of order, but the dates have the correct items in them. So, all right, so fall break's the 19th. That's when we don't have class. Following Tuesday, we'll use that time to review. Thursday, I put you on the spot with the test. That's on chapters 2 and 6. The final will cover chapters, well, it's technically comprehensive, but it will focus primarily on chapters 8 and 9. So it's time that we all literally get on the same page. And that's why, dang it, I want homework 2 finished. So Okay, now, with that in mind, do we have questions on any aspect of homework 2? Yes? Oh, I thought you were raising your hand, sorry. Okay. Uh, anybody?
For exploration 2.2.3, I kind of lost the way to borrow.
Okay, 2, 2, 3. Okay. Yeah, so this is testing your understanding of the various parameters of a floating point system. So a floating point system can be described by 4 items: the base, the precision, which is really the number of significant digits, and then the range of exponents, L and U. So here you're given that the base is 10. So, for the precision, so the P part, how many significant digits would this floating point system require to be able to represent both of these numbers exactly? So for instance, if you see, because all of the significant digits go into the mantissa. So as an example, like right above, actually, I'm going to go here. Okay, so as an example, actually, this is a good example to look at. Let me make this a little bigger, because it addresses the P part of a question. That this number has 9 significant digits. So in order to be able to represent it exactly, you have to have P at least equal to 9 for that to work. Otherwise, if you have, let's suppose I had 7 digits. So if P is equal to 7, then what I have to do is I have to truncate this after 7 digits. So I'd have to have 1.23456 not 7, because I'd have to round. And so I'm settling for an approximation of x in that case. So you have to look at both of these numbers, see how many digits you need for each, and take the maximum of that. So then your mantissa has the capacity to store all of those decimal digits. And the thing is, it doesn't matter whether digits are on the left or right of a decimal point. You need them all, at least all non-zero digits, to represent exactly. Because what you're going to do with each of these is, actually what I would recommend is you first rewrite both of these in scientific notation. So have so for instance, this one would be like 2.3948723 times 10 to the appropriate power. And that's similarly for this one, where it would be times 10 to a negative power. And once you do that, then you have the exponents that are required to represent these two numbers. So L and U define an interval into which all exponents must fall. You can't have any exponents outside of that range. So those numbers would be outside that range, would be too large or too small to represent. So so the exponents needed to write these in scientific notation, normalized like is done in this example right here, is what you would need for L and U. Because every floating point system accommodates a range of magnitudes. And that's what we want to see here. What range of magnitudes do we need for these two numbers? Okay. Before anyone else asks anything, a preemptive comment on, because this is based on a question I got on by email. This exploration 225. This is not a MATLAB question. This is just applying the definition. So there really isn't much to it. And I should mention that if you go ahead and use this definition to get the value, like working it out on paper, and then you actually type this expression as is into MATLAB, it'll overflow. And the reason why is, how is MATLAB going to compute this? That's going to be based on what you typed in. It's going to compute beta to the u plus 1 first. Well, u plus 1 is outside of a range of allowed exponents. So just computing this right here is going to cause overflow. It never gets to the point of multiplying by this. But here's what you can do. You can rewrite this as beta to the u, which is fine. That can be represented. And then you take the other rest of it, beta to the first power, and distribute it through here. So in other words, I can write this as beta to the u times beta minus beta to the minus p plus 1. That can be represented. Now again, this problem is not about that, but this is how you would handle it if you wanted to represent that number. Because what's happening here is, like if this were decimal, for example, you would have 10 raised to the largest power you can get times this mantissa, which would be like 9.9999999 to as many nines as your precision allows. So you stop just short of going to the next power, which would not be allowed anyway. Okay. All right. Whereas one of the later problems, whoa, stop that. This one is about playing around with these things in MATLAB, because these are not the actual parameters of the IEEE floating point system. Very, very, very close to it is what you would get from the same storage. 1 bit for a sine, 11 bits for an exponent, 52 bits for a mantissa. But you'd have to play around with this a little bit to see. That's what I wanted you to try in this problem. To see what are the discrepancies between the floating point system, the abstract floating point system described in this table, and the actual floating point system that MATLAB and really all computers rely on. Okay. All right. Other questions? Nice to see questions about 2.2 for a change. Indicates progress. So in other words, I'm going to get a bunch of them on Thursday? That never happens. I always think it'll happen, and it doesn't happen. So then I could, what? Yes, it does. So then, and of course I also know better than to assume that that is a sign that everything is going swimmingly with this assignment, or whatever assignment it is. I've been here for 8 years. It's the same pattern that happens in every class. There's a handful of you that ask questions regularly, and then the rest it's crickets. Even though but the thing is, the ones who do ask more questions are often the ones who end up doing better in the class. I think the only exception might be if someone who happens to be exceptionally well prepared for the class to begin with, which is, sometimes that happens, but not very often. And I can certainly understand that, it has also been my experience in 8 years, that practically every student at USM is I don't know, frightened to death of their professors. I don't know. I try not to be threatening, but maybe there's just no way around it because of the nature of my position. But I will tell you that that is in no way a part of a recipe for success. And I can speak to that firsthand because, in high school, I had a history teacher / track coach. Yes, I was in a track team, who was also the football coach and dedicated his life to being an exact clone of Vince Lombardi. And seriously, his voice sounded like him. He even had the same fiery temper that could be explosively set off in an instant. But I would still challenge him on things. If there's something I felt wasn't right, I would talk to him about it. And of course, I was as afraid of that as anybody else. But I did that anyway because simply it was the right it was the right thing to do. My doctoral dissertation advisor, Gene Golub, who he passed away 10 years ago, but he was the foremost, I would say, the foremost researcher in the world on numerical linear algebra. People were, us graduate students were quite frightened of him too, but when I felt that he was being unreasonable, because okay, sometimes he could be an ass munch. Pardon my language, but and I would call him out on it. And the funny thing is that he did not vaporize me, as you can tell. But more than that, he actually respected me more. And I echo that here on one of the first days of class, that I have more respect for a student who, number one, is willing to put themselves out there to ask a question that I pose in class, even though they're not sure if they have it right, but at least they gave it a shot. I also have more respect for a student who they may feel uncomfortable for grasp of material, and they might be concerned about what I might think if they show me where they're at, like if they're struggling with a problem, for instance, and then I don't know, are you afraid that I'll declare you a hopeless case or something? Because I don't work that way. I see where a student is at the present time and help them grow from there. And in some cases, grow substantially, especially if I have an opportunity to work with a student long enough. And a lot of evolution has happened as a result. But so, and plus, there are not too many things really that piss me off. So here's the list. And it's a very short list, but I like to think that it's exhaustive. And number one is when students give up on either themselves or me. If they simply assume that they're not going to get it, or if they assume that I'm not going to be able to do anything for them to help them get it. And that really goes with item number two, and that is, if I am, if students through their being uncommunicative or fearful for whatever reason, deny me the chance to fully do my job. Not just the part of the job I'm going to do anyway, and that is getting up here in front of you all and lecturing and assigning problems, but the real part of the job, and that is helping you guys get it, helping you guys develop. When I'm denied a chance to do that, yes, that pisses me off. It's not fair to you guys, to yourselves, or to me. And that also applies to, for instance, if there's something I need to do a little differently, but someone doesn't speak up, and therefore, because I'm incapable of reading minds, it goes unaddressed. For example, how I type too fast. Right? Yeah, as I found out yesterday. Now, I don't know how long that information has been sat on. It should not be sat on at all. It should be brought into the open immediately. And better late than never, so yes, I will try. But I need your help because I even watched my video from last class. I hear him looking for a phenomenon, and it's not something I can obviously detect. And especially when I'm up here, my IQ plunges 50 points, and I'm kind of in the moment. I don't like that aspect of teaching, but it's just the way it is. It's just the way it goes. You kind of go on autopilot, and that's why some level of preparation is important, or just really knowing your stuff. But again, I need your participation, and I've said it a few weeks ago. Always choose a path of being more communicative rather than less. It will make all the difference in the world, and that goes to the final thing that pisses me off, and it really is a final thing, is when advice I give like that, based on long career of being successful in spite of challenges that would send chills down your spine, that advice should simply be rejected out of hand, as if I don't know what I'm talking about. Because in these cases, I do, so please at least consider it. That I tell you these things for a reason. So, okay, now, I don't know if my ranting has given the time that has consumed has led anyone to come up with any further questions on the homework. Yes. Oh, is that Ross?
Yeah, I just want to let you know, see, I was in the library doing the homework,
Okay, and thanks for letting me know that. I was going to check later anyway. Yeah, Megan. 0.16.
16.
Okay. Close to the end. That's good. Okay. Yes.
I was wondering, this is probably a bad question, but n.
There are no bad questions.
Oh. For n, is that like a random number you would pick?
Oh, okay. Oh, no, okay. N is 1,000 in this case. Yeah, it's how many numbers you have. And I actually picked that randomly. Actually, another thing I want to mention about this particular problem is, all right, so this function rand n. So unlike, because rand, those of you who care about statistics at all and probability distributions, rand gives uniformly distributed random numbers, whereas rand n gives normally distributed random numbers. So the default usage of rand n uses a standard normal distribution, mean 0 and standard deviation 1. But what you can do is you can use scaling and shifting. So you can take these numbers generated by rand n, multiply them by 0.1 to account for standard deviation, and add 1,000 to account for the mean. So that's how you get your numbers in the first place. But the thing to keep in mind is, even though it's pulling from, so what you're doing is you're generating a vector of random numbers that is pulled from a normal distribution with mean 1,000. However, that does not mean that the actual mean is 1,000. So this x bar here refers to the sample mean. You need to actually compute that. Don't just assume it's 1,000, because that'll throw your code off. And the way you can do that is just use, there's a couple ways to do it. You can just use the mean function. So if you have a vector x and you say mean of x, that'll give you the mean. And all it's doing is that's the same as summing them up and dividing by n. Okay. Okay. And the thing is, when you go ahead and implement these formulas, if you're not sure if you're seeing what you're supposed to see, because maybe there's something wrong in the code that you use to generate them, you can always check with me. Go ahead and send me what you have, and I'll say, okay, yes, you observed the right effect, or no, you did not. Once you, because I don't want to give that away, but once you do observe a right thing, then the question is, what is causing what you see? And think in terms of floating point arithmetic issues. And there are really only, in any of these problems, there are really only two issues in floating point arithmetic to consider. One, is it an issue of overflow, or is it an issue of catastrophic cancellation due to a bad subtraction? And the parameters of these random numbers, mean 1,000 or standard deviation 0.1, are chosen to highlight one of these issues, because what do these numbers look like? They're all pretty large, but narrowly clustered around 1,000. When they're all really close together. So, which would produce the effect that I want you to see, because any other random numbers might not do that. Okay. But yeah, I don't judge questions as good or bad. So there's asked and unasked. That's my categorization. Are there any more? I guess that means good and bad, but okay.
I have another question.
Yep.
It's on x right from 2.2.6.
6?
Mm-hmm.
Okay. Yep.
Is that dealing with the underflow and overflow? I kind of got confused when I saw the 100 pi or another.
Wait. Oh, hold on a second. Oh, okay. All right. Yeah, I was just using 100 pi as an example of any old number. Didn't really matter which one I chose, but I wanted something that would have a lot of decimal places to it, because pi, of course, has infinitely many decimal places. So if you think about 100 pi, okay, so 314.15926, etc., but you're going to represent that in a 5-digit floating point system, so you have to round that to 5 significant digits. But that's not really what the focus of a problem is. This is about the fact that if you normalize floating point numbers, then the representation of them is unique. Whereas if you don't, then you can have several floating point representations of the same number, where because you can move around, you're free to move around a decimal point and just adjust the magnitude accordingly. So that's really what the focus of this problem is. And to illustrate that a little more, like this number right here, if I have a normalized floating point number system, I can't write the number this way. I have to move this decimal point past the 3. I'd have to have 3.4394 times 10 to the negative whatever. But I could also write this as this exactly as it is times 10 to the 0. So that's not allowed if you normalize. It is normalized. It is allowed if you do not normalize. Now, IEEE floating point numbers, they most of the time are normalized. There's one exception, is that when you go to the smallest allowed exponent of minus 1022, then it switches to no longer be normalized. And the reason for that is, well, there's a couple reasons, but one is, so you can actually represent 0. It seems kind of strange that if you normalize floating point numbers, your mantissa is at greater than or equal to 1. That means you can never have 0 exactly. But by not normalizing what's called gradual underflow, that means that if you have this floating point number represented in 64 bits, and all the bits are equal to 0, then it actually gives you 0, which you would think only makes sense. In fact, you have 2 representations of 0. Can anyone think of what the other one might be? So like you have no exponent, you have no mantissa, there's nothing there. What's left? What are the 3 pieces of a floating point number? I'll put the definition back. What? Oh, no, not the base, but because the thing is, like as far as like how the numbers are stored, we have a certain number of bits set aside for mantissa. We have a certain number of bits set aside for the exponent. The sign bit, yes. So in other words, if I have, okay, so here's what I can do. If I go to format hex, and I'll just type in 0. Okay, all zeros. That's what you'd expect. I can do this. I'll see if MATLAB will take it. -0. Yeah. So look, there's an 8 there. So, okay, so in binary, what does that mean? I have to, this is a hex digit, so I have to break this down into 4 binary digits. That would be 1, 0, 0, 0, and then all the rest zeros. I'm not going to type them all out. So that 1 is the sign bit indicating that this is a negative number. So now for purposes of arithmetic, it's exactly the same. I mean, you feed either 1 into any sort of circuit for arithmetic, addition, multiplication, whatever, it won't affect the result, but now we have 2 representations of 0. Okay. But yeah, for that one exploration, number 6, I could have picked any number for that. Other questions? Yes. Okay. Okay, so you're asking about both. Oh yeah, I can see that. Okay. All right.
Like I get that overflow can occur from squaring.
Yep.
Like that, but I just don't. I can't see how you would rewrite that and it fix the overflow.
Okay, this is why I gave you a hint of trying to factor something out. Because, okay, well, All right, I'll give another hint. Because I said earlier, you can assume without loss of generality that x is the larger of the two. So let's take that to a logical extreme.
So you like approximate x, say x approximates y?
I'm sorry, what? No, not like that. No, I mean, just that, to simplify how you describe what you do, just go ahead and assume x is a larger, because otherwise you have to have two cases. If x is larger, do this. If y is larger, do that. And they're so similar, it's not worth talking about. But this leads me to another hint, and that is, how would you handle this? How do you rewrite the expression if y is equal to 0? So just toss y out. Then the expression as written, square root of x squared, is still, bless you, still problematic. Bless you. But by tossing y out, I'm hoping that this will give you an idea of what to do. Figure it out for that case first, and then put y back in and try doing the same thing, which you actually will be able to do. It just takes a little more algebraic manipulation. But yeah, because this expression as written, you can't simplify it really. But if y is out of a picture, you can. And then you can generalize that to when you put y back in. So give it a try. And then if need be, we can talk about it again on Thursday. All right. But then once you have that worked out, then the idea is you can see what to do about the more general case where you have n numbers instead of just 2. And it still involves working with the largest one. So that's what your solution will involve. And you can just make an assumption as to which one is the largest and just go with that. Like assume x1 is largest. All right, this is good. Anything?
I emailed you a question right before I came to class.
Okay.
It was on number 7.
Wait, number 7? Did I hear you right?
Yeah.
Okay.
It's normalized, meaning that it can't be elevated. It must not be non-zero. I'm kind of.
Oh, okay. A normalized number means the leading digit has to be non-zero.
Okay.
Yeah. So for example, that is not normalized. So you'd have to shift. You have to write this as 3.4394 times 10 to the whatever. Whereas if you express this as a non-normalized number, well, actually you could express it as exactly this, and that's non-normalized. Oh God, I hope I didn't get that backwards earlier. You have to watch me about those things. One of my former students said that a mathematician says A, writes B, and means C. And I thought, no, I don't do that. And then I found otherwise. It's very sad. Okay.
So I don't understand, like, on expression 2.2.4, it's, what if the way I wrote my answer wasn't,
Oh.
the leading number was non-zero?
Okay. So, all right. So here's what you can do, and this kind of goes into what's going on with this definition here, because the value of this depends on whether the number is normalized or not. Okay. So here's what you can do is, all right. So in this example with 5 digits. If the numbers are normalized, which we're not assuming in this problem, it comes up in problem 7. If the numbers were normalized, then the smallest mantissa you can possibly have is 1. Because that leading digit has to be non-zero. But suppose you don't have that requirement, numbers are not normalized, then in the case of 5 digits, you could have like the equivalent of 10 to the minus 4. Okay, so if I go back to the definition, here's your mantissa. So normalized numbers, d0, which is multiplied by 1, has to be non-zero. So that's why, and then all the other digits are allowed to be 0, so that's why your smallest mantissa is 1. But let's suppose that these DJs can be anything you want, no restriction. Then, look here, what is your smallest mantissa? It's 1 times your base to the most negative power you can have, which is minus quantity p minus 1. So, when you normalize, the smallest number you can represent is determined exclusively by your exponent range. When you do not normalize, it's determined not only by your exponent range, but also how many digits you have in your mantissa. And this is why, I go to do an example in MATLAB. Okay. For this floating point system, the exponent range is minus 1022 up to 1023. So minus 1022 is the smallest allowed exponent. So of course I could do 2 to the minus 1022, and that's fine. Whoops, I need to go back to format long. Remember, tell me if I'm typing too fast. Okay, so you have a representable number, but then you think, oh, that means I can't go smaller, right? Well, go ahead, go smaller. You can. And you can keep going. So if I go to 2 to the minus 1074, that's representable. But if I go one step further, 2 to the minus 1075, it says, oh, you've underflowed. And why is that? Why is minus 1074 a magic number? It's equal to 2 to the minus 1022, which you get from the exponent, times 2 to the minus 52. In this floating point system, p is equal to 53. That's the precision, because you have 53 digits in your mantissa. So the smallest power that goes with them is 2 to the minus 1 less than that. And that goes with the definition. If power is going from 0 up to negative power is going from 0 up to p minus 1. So that's how you figure out the smallest positive number in a non-normalized system. Okay. Any other? Okay. All right. Back to polynomial interpolation. And what I'm going to talk about today is, well, two items that go together. If I use a polynomial to approximate a function, how accurate is that approximation? And the second thing is, how can we reduce the error? And why this is a serious issue, I'm going to illustrate using actually a very famous example. I'm going to work with a function, f of x is equal to 1 over 1 plus x squared on the interval minus 5 to 5. We're going to approximate by a degree 10 polynomial. So whatever degree you have, you need to fit your function at that many points plus 1, just like 2 points determine the equation of a line, which has degree 1, or 3 points determines a parabola. So here are the points I'm going to use. Very convenient choice. The integers from minus 5 to 5. Okay. Now I want to remind everybody, we have, to make sure you get all the information that I present here, course, you have a diary. You also have a video. So you might want to consider not. I hope you're not scrambling to take things down during class. The other thing is, the higher level of a class, the less I expect you'll be able to absorb everything that's presented during class. The higher level of class, the more necessary it is to go back later and pick up things. But I'll still try to go at a reasonable speed, but just nothing gets lost, really. Okay, now I'm going to construct my polynomial the easy way by letting MATLAB do the work. So my x values will be from -5 to 5. I'm going to define a function handle. You saw this in homework 1. 1 over 1 plus x. I'm going to use dot operations here, dot divide, and then 1 over 1 plus x dot squared. And the reason for that is I want to be able to pass vectors to this function and have it work. So my y values, I'll just do f of x. So now I have 11 x values and I have 11 y values to go with them. And now I can do polyfit. Polyfit will, so I pass my x's, pass my y's, and the degree is 10. So I specify that as a third argument. And now I have, well, I'll show you p. These are the coefficients of that polynomial, which don't really mean very much, but well, this last one, 1, that's at x equals 0 is the value there. Notice every other coefficient is 0, like the odd degree coefficients. And the reason for that is 1 over 1 plus x squared is what we call, and you'll learn this in Cal 2, an even function. Does anyone remember what an even function is? If you don't remember a formula, like what the graphs look like. What? Sine is an odd function. Cosine is an even function. Okay, so f is an even function. I'll do a little Cal 2 review. F of x equal to f of minus x. For example, even powers of x. Also cosine. The Taylor series for cosine is consists of even powers. Odd function, f of x is equal to minus f of minus x. So you negate the x, that negates the y. So for instance, x cubed, x to the fifth, and so on. Sine, and therefore tangent. Okay. Derivative of an odd function is even and vice versa. Odd functions are nice for integrating. You integrate an odd function from minus a to a, and the answer is 0, and so on. We'll see more of these later. Okay. Now, here's what I want to do. I want to graph the function, the original function f, and the polynomial. So first, the function. I need a bunch of x values, like a ton of them, from -5 to 5. I'll do a spacing of like 0, 0, 1. Okay. And I put an s here. This is how I like to name variables. I'm pluralizing. This vector has a bunch of x's. Okay. And then, okay. My y values will just be f at those x's. So now I'll go ahead and plot. And I want this to be in blue. Okay, so there's our function. Next, what I'm going to do is, well, hold on, I'm going to superimpose. And I'm going to plot the x values and y values that I use for interpolation. And I'm going to plot those using black circles. So K for black and then O for circles. And this just shows the interpolation points on the graph. Now, for the good part. I'm going to plot the polynomial, so for my x's, and I'm going to use polyval to evaluate my interpolating polynomial at those x's, and I'll plot the curve in red. Well, that went well. So you can't assume that just because your polynomial agrees with your function f at selected points, notice it agrees with the blue curve at all of the points that are black circles, don't assume that it's a good approximation of your function everywhere on the domain. Now, near 0, it's fine. But as you get near the boundary, this error is ridiculously large. So I'm doing this to motivate why we need an error formula. So we like to be able to estimate the error in but when we approximate a function f of x by this interpolating polynomial of whatever degree we have. Now, to get the error formula, well, I'm not going to like derive a whole thing here. In fact, to a certain extent, you will in one of the explorations, and I'll talk about that momentarily. Okay. So for inspiration, I will recall something you've been using anyway, Taylor's theorem. Okay, here's Taylor's theorem. Now, here we have our nth degree polynomial approximation of f. So then you can rearrange this and say f of x minus the Taylor polynomial is equal to this remainder Rn of x. And that's what we have here. I have it in two forms. This is the integral form and then the non-integral form. This is the one that I want you to focus on. Now, one of the things about the Taylor polynomial is it matches f at x naught. It also matches its derivative at x naught, and then its second derivative, third derivative, etc., all the way down to the nth derivative. So you can think of it as doing like a n+1 fold interpolation of f all at one point, x naught. Whereas what we're doing is different. We have n+1 distinct points, and we're only matching f at them. We're not matching derivatives. We will talk about matching derivatives on Thursday, though. But look at the remainder. The remainder is like the next term in the polynomial approximation. We have an n plus first derivative. The only difference is it's evaluated at this unknown point, and we divide by n+1 factorial, and then we have x minus x naught to the n+1. Now, it turns out that the error formula for polynomial interpolation has a very similar appearance. So just to contrast the two, okay. So to summarize what I just said about Taylor polynomial approximation. Okay, so f of x minus my nth degree Taylor polynomial, Pn, is equal to Rn. And what we have here is the form of your Taylor polynomial approximation is a sum from j equals 0 up to n. And what do we have? We have coefficients. We have a jth derivative at a point x naught. And then we, I want to put my subscripts in, divided by j factorial, bless you, x minus x naught, all raised to the j. So that I'm just repeating Taylor's theorem here, but I want to have everything in one place. The error formula, like I said, almost the same as the next term. And I'm going to put in a question mark to reflect if this is an unknown point. Divided by n+1 factorial, and then we have x minus x naught to the j plus 1. Okay, so that's the Taylor situation. And Pn, what it does is it satisfies these conditions. F of x naught, or sorry, Pn of x naught equals the value of f at that point. Pn prime equals f prime at x naught. And you keep going. I could go like second derivative and so on. All the way to the nth derivative. All right, so those are the conditions that this polynomial is satisfied. And here's the error. So now I'm going to show you the error for polynomial interpolation. and also the form, because again you can see parallels between them, and I want to point those out. So f of x minus, I'm going to use a lowercase p, and now this is for the polynomial you get using either Lagrange interpolation or Newton interpolation. It doesn't matter because the interpolating polynomial is unique. The method doesn't matter, it produces the same polynomial. And so I'll describe what the error is momentarily. Now, what does the interpolating polynomial look like? I'm going to work with the Newton form because it's most similar to the Taylor polynomial. So it's a sum, again, and we have a divided difference, f square bracket x naught, x1 up to xj. So this divided difference takes the place of jth derivative over j factorial. And then, I'm going to need to make this bigger. Times a product of linear factors, x minus x naught, x minus x1, up to x minus x sub j minus 1. So instead of having x minus x naught repeated a certain number of times, like raised to a power, you have a bunch of distinct linear factors multiplied together, which makes sense because a Taylor polynomial only approximates f very thoroughly at one point, x naught. Pn matches f at several points, so that's why we have several distinct linear factors. Now, one thing I want to point out is in the book, Theorem 6.3.3, let me check that. Come on, where is it? Yeah, this right here, Theorem 6.3.3 says a divided difference is equal to the corresponding derivative at an unknown point over the corresponding factorial. So I want to call your thing is in this. I have an exploration in here to prove this theorem, but I did not assign it. You're welcome. But you can. But I have a later exploration where you have to use this result to prove something else. The error formula I'm about to show you. Okay. Now, here I have a divided difference times all these factors. Here I have a jth derivative over j factorial times all these factors. And I've just shown you the theorem that says that a divided difference that's equal to the derivative, that same derivative at an unknown point over j factorial. So what I'm saying is these coefficients here and in here, they're almost the same. The only difference is here the derivatives are evaluated at x naught, that's fixed. Here they're evaluated at some unknown point. Okay. But they play the same role. Okay. Now, what is the error? It looks like the Taylor remainder in a way. It's equal to the next derivative, n plus 1, at an unknown point, divided by n plus 1 factorial. And then, where we deviate is right here. Instead of having x minus x naught, oh, this is bad. What should this be? It should not be j. If this is a remainder r n of x, what should be here? N, yeah. I'll fix that in the diary. So instead of having n plus 1 factors here that are all the same, we have n plus 1 factors that are all distinct. X minus x naught, x minus x1, x minus x2, and so on, up to x minus xn. Okay. So that is the error in polynomial interpolation, and this is found in Theorem 6.4.1. So I'll just show you that now so you can see it more cleanly. Yeah, right here. So here's the error in the interpolating polynomial. So This part looks exactly like the Taylor remainder, and then we just have these distinct linear factors instead of a repeated linear factor. But you still have n plus 1 of them altogether. It's just the product of x minus each of the interpolation points. Now, what I assigned in this homework, homework 3, is this exploration. To prove this theorem, it's not as difficult as it sounds. I will tell you, it is absolutely not a long proof whatsoever, especially because, as I point out here, this follows from 633, which I'm not asking you to prove. You can just use the result, go ahead and take it for granted. But I'm going to give you a quick roadmap here in this diary. (6.4.1) proving theorem 6.4.1. So here's what you do. So you assume that Pn of x interpolates f at the given points, x0, x1, etc., up to xn. And then we come up with a new interpolating polynomial. And this is in the hint that I give. Work of the interpolating polynomial for these points, x0 up to xn. And then we throw in one more, x. Now that seems odd because x, you think of x as a variable. But for our purposes, we're thinking of it as some fixed value x. We don't make any assumption as to what it is. But whatever it is, you can just go ahead and use it as an interpolation point. So Pn plus 1 of x at these same points, and then we throw in one more x, and write in Newton form. And the reason why is you could say that Pn plus 1 is equal to Pn plus, and then what you do is, what you have here is the next term in the Newton form. And what does that involve? It involves a divided difference. It involves a product of linear factors. And you use the fact that Pn plus 1 of x is equal to f of x. Why? Because we're actually using x as a new interpolation point for Pn plus 1. So we have that agreement. So here, I can just replace this with f of x. So now I can say f of x is equal to Pn of x. So this question mark, this part here for question marks, that's the error. You just have to sort out what that is. So again, not a long proof. You write some big long thing, you've gone the wrong way. So this is about taking a few pieces and putting them together in the right way to get what you're after. Okay. So the thing is, what we would care about now, and hopefully I can do enough of this in the time we have, or maybe I can let some of this spill over into Thursday. Here's our dilemma regarding the error. Why is it large? I get the example I showed you of 1 over 1 plus x squared. It's ridiculously large. What went wrong? Now, the thing is, these derivatives, they could get large. That's one thing that you can't really get around. It just depends on your function. But let's take a look at this part here, x minus x0 up to x minus xn. So here's what I'm going to do is I'm going to create a new figure window. And I'm going to take just this part of the error, x minus x0, x minus x1 up to x minus xn. And I'm going to plot that. And let's see how big that can get. For xi is equal to minus 5, minus 4, etc., all the way up to 5. All the interpolation points that I used for that example. So what I'll do is Well, first I'll form this polynomial. This is a polynomial of degree 11 with roots -5, -4, etc. up to 5. So I can go ahead and make that polynomial using a poly function. I know what the roots are, -5 up to 5. And now what I can do is plot, using my x values and polyval, I'll plug those x values into this polynomial. Okay, so this is a figure window where I want it to go. And yeah, that's pretty dang big. So that alone gives us an idea of why this approximation of 1 over 1 plus x squared was so dang inaccurate. Because as we see, when we get near 0, it's not bad. But again, as we get close to the boundaries of our interval, it was atrocious. And the moral of this story is high degree polynomial interpolation with equally spaced points. Don't do it. It does not go well for you. Now, the high degree part makes sense because if you have a polynomial of a high degree, say degree 10, 20, or even 100, well, that can have many roots. Like a polynomial of degree 100 can have up to 100 real roots. What kind of graph would a function like that have? Like just from the look of it. Like a function that has a lot of roots. Like if you can use it to describe, even in whatever words you like, what a graph like that would look like. What? Spiral? Okay. Interesting. Yeah. Yeah, very curved. Yeah, oscillatory. Yeah, it's all over the place. Kind of like, well, whoops. Well, here's a little oscillation here, but if you get a higher degree, it would be more oscillatory still. Whereas look at our function that we're trying to approximate, 1 over 1 plus x squared. That's not oscillatory at all. It's very smooth. So that's the problem, is that the polynomial we're trying to use to approximate may have a very different character in its graph than the function you're trying to approximate. But it's having high degree by itself, that's not the deal breaker. It's a fact that it's equally spaced. And to show you why, I'm going to try a different approach. Use different x's in order to make this polynomial x minus x naught, x minus x1, etc., up to x minus xn, as small as possible. So it turns out to be easier than you think to make that a manageable size. Using one of my favorite entities in numerical analysis, I think these things are pretty dang cool, and it's too bad I can only spend 9 minutes on them today. Chevy polynomials. I'll have to continue this on Thursday. Now, here's what a Chebyshev polynomial is. I'm going to assume x is between -1 and 1. So absolute value of x is less than or equal to 1. So we're just going to focus on -1 to 1. Here's my definition of a degree k Chebyshev polynomial. I'll call it tk of x. And this is discussed in the text further down. You can read it more about them here. Well, here's a definition right here. A kth degree polynomial is cosine of k inverse cosine of x, which is about as unpolynomial-like as you can get. So you might be thinking, how on earth is that a polynomial? Well, let's take a look. So I'll fill in this definition. Cosine of k inverse cosine of x for x in this interval. Outside this interval, you have to adjust the definition using like hyperbolic cosine, but we won't get into that. So let k equal 0. What do you get? How does this simplify? Give it a shot. Cosine of 0. What is cosine of 0? 1. Yes. Okay. What about t1? How does that simplify? Think about how functions and their inverse functions relate. Ooh, this came up before. You know, like other inverse function pairs, like e and log or square root and squaring. Anybody? Cosine of inverse cosine of x. Yeah, simplify. Yeah, so cosine, and the k is 1, so inverse cosine of x. That's just x. So far we do have two polynomials, 1 and x. Now, but what about after that? Then it gets a little trickier, but we have, believe it or not, trig identities to help. And this is actually subject one of the exploration, so I won't spend much time on it here. But basically what you do is, using these trig identities for, and actually I remember my colleagues at the department pointed out there are really only 3 trig identities you need to know. There's cosine squared plus sine squared equals 1, which is the only trig identity that most students remember. And then there's for cosine and sine of a sum or difference. Once you know those, you can pretty much derive all the rest of them. So here we use them by applying them to this definition right here, and we get this relationship. It's a 3-term recurrence relation, which means each one depends on the previous 2. So for instance, the next one, t2 is equal to 2x times t1 minus t0. Well, let's fill in what that is. t1 is equal to x, so that's 2x squared. And then t0 is equal to 1, so we get 2x squared minus 1. I'll do one more. t3 is equal to 2x times t2 minus t1. So that'd be 2x times x squared, or 2x squared minus 1, minus t1, which is minus x. So then you can multiply all that out, and you get 4x cubed minus 2x. And what you would notice is that the coefficients, leading coefficients, are powers of 2. You have 1, 2, 4. It keeps doubling because of the 2 in the recurrence relation. Another observation is that odd-numbered polynomials have only odd-degree terms. Here we have x. Here we have 4x cubed minus 2x. Even-numbered polynomials have only even-degree terms. So here we have 1, and then we have 2x squared minus 1, and so on. And these properties are quite convenient for a lot of things. But here I want to talk about how they're useful for reducing the error. Suppose we choose the interpolation points xi to be the roots of t n plus 1 of x, because we have n plus 1 points, x naught to xn. So I need to get, these polynomials will have n plus 1 real roots. And the thing is, here's what we can do. I can set cosine of n plus 1 inverse cosine of x equal to 0. So how do we figure that out? It's easier than you think. You use your trig. You use your knowledge of where cosine is equal to 0. So it turns out what you want is whatever's inside has to be a root of cosine. So n plus 1 inverse cosine of x must be equal to an odd multiple of pi over 2. Because those are the points at which cosine is equal to 0. So now I can just solve for x. So x turns out to be, I move the n plus 1 to the other side, and then I take cosine of both sides. And what you get is 2j plus 1 over 2n plus 2 times pi. And to make sure we have distinct roots, we just let j equal 0, 1, 2, up to n. So these are called but Chevy points. And those are described. Okay. Well, these are for zeros of tk. I wrote the zeros of tn plus 1. So if you let k equal to n plus 1 and shift the index, you would get the same formula. But it's derived in exactly the same way. Okay. So now, so it turns out that all of these angles are equally spaced. But then we take cosine of them, and you get points that are not equally spaced. So here's what I'm going to do. I'm going to create a new figure window. Hopefully, I'll try to do this in 2 minutes. Bear with me. And I'm going to let my x values be cosine of 2 times 0 to 10, because I have 11 points, plus 1 over n is equal to 10, so I'll fill that in, times pi. But I'm going to multiply by 5, because the Chebyshev points are they're cosines. So what range of values would cosine give me? I know you know this one. Well, the cosine by itself. -1 to 1. So I need to multiply by 5 to get points between -5 and 5. So those are my points. And then I have my y values. I'll plug into f of x again. So I'm going to repeat what I did at the beginning. And then what I'll do is, okay. So my new figure window, figure 3, I want to plot my function. Okay, there's my function. Hold on. And then I'm going to plot my x values, my y values in black circles, like I did before. Notice, how are they distributed? Before they were equally spaced, but what do we observe now? Yeah, they're clustered at the boundary, which is helpful because where was the error bad? Before, at the boundary. So now we put more points there. Okay, now I'm going to plot my new polynomial, which I actually need to compute. Hang on. Polyfit, x, y, and then degree 10. And now I will plot my x values, plug in those x values into the polynomial, and I'll plot it in red. There. Still not fantastic by any means. It's a whole lot better than it was. Whoa, what happened? There it is. Okay. Not sure how I made it disappear. So at least the error is manageable. Now, why is that? I'm going to have to tell you on Thursday because I'm out of time. Or you can read about it in the section 6.4.2, what causes that product of linear factors to be minimized. Okay, so keep doing best in homework too. Keep questions coming by email, if not in class. Remember, be more communicative. Dang it.
I was wondering, the university